Organic chemistry is concerned with the compounds of carbon. So the starting point is the carbon atom and the bonds it can form. In the simplest example, methane, carbon bonds with 4 hydrogen atoms. But it is the unique ability of one carbon atom to bond to another that is the basis for the amazing variety of organic molecules. When the carbon atoms are linked by single bonds, there is great freedom of movement and the groups are constantly rotating. This movement is prevented when the carbon atoms are linked by a double bond. A double bond does not allow rotation of one carbon atom relative to the other, so the hydrogen atoms can't move out of position. This restriction of movement has important consequences in larger molecules. Any groups attached to the double bond are also fixed in position. So molecules made up of exactly the same atoms can have quite different shapes, a phenomenon known as stereoisomerism. Shape has a profound effect on the properties of organic molecules. Every year in the United Kingdom, thousands of tons of crops are lost because of insect pests. One major group of pests is the aphid family, a family which includes the common greenfly and blackfly. As well as feeding on the growing plants, aphids are responsible for spreading a variety of plant diseases. So it's not surprising that farmers expend considerable efforts to remove these pests, usually by spraying with toxic chemicals. But this crop, which is receiving its autumn spray, is being treated in a different way. In fact, these plants are being sprayed with a substance that is an exact copy of a compound the aphid produces itself. Aphids cluster underneath leaves, from where they attack the plants. Under here, they are comparatively safe from pesticide sprays. To kill them, some means of bringing them out into the open is needed. Scientists at Rothamsted Experimental Station in Hertfordshire, led by Dr. John Pickett, have developed a method of doing this. It's long been known that when an aphid is disturbed, it produces a liquid secretion from a gland on its abdomen. If this secretion is collected and placed near other resting aphids, it causes them to scatter. The secretion contains some kind of chemical messenger called an alarm pheromone. This warns other aphids of possible danger. Spraying the secretion containing the alarm pheromone onto the crop would flush the aphids out, making it easier to kill them. But this method wouldn't work commercially, as the aphid only produces the secretion in minute quantities. The answer is to synthesize the pheromone in the laboratory. But first, the secretion must be analyzed.
Well, having isolated the sample from the aphid, the job now is to identify the individual components. And we do this using gas chromatography. This is a gas chromatograph, and it contains a capillary tube which is responsible for separating the individual components of the mixture. As the individual components emerge from the gas chromatograph, they pass into the source of the mass spectrometer. Now, in the source of the mass spectrometer, they're bombarded by electrons from a filament, and this converts the molecules into ions. The ions are then repelled out of the source and pass through the poles of this electromagnet, which allows us to measure their mass. And then the data are processed using a small computer. We now inject the sample from the aphid into the capillary column. This is done using a fine bore needle which goes all the way inside the capillary tube and letting the sample run through and be separated by chromatography. Well, we now have on the screen the gas chromatogram obtained by the analysis of the aphid.
Each peak on the graph represents one of the compounds in the mixture. The height of the peak shows how much of the chemical is present, and the horizontal distance is the time taken for it to emerge from the gas chromatograph. The numbers on the top of the larger peaks are the times. For example, the chemical with the highest peak was retained in the capillary column for 471 seconds. The analysis shows that there are many chemicals in the mixture. The question is, which one makes the aphids scatter?
Well, this cosy little setup allows us to identify the active components from the aphid. We've got a conventional gas chromatograph and monitor, and here we have a preparation using a live aphid.
At the heart of all this equipment is an aphid, which is fixed to a perspex plate. Aphids detect the active chemical using a kind of nose on its antenna. A small electrode inserted in this nose picks up an electrical response the aphid makes when it encounters the alarm pheromone. Once again, the chemicals in the secretion are separated using a gas chromatograph. Each in turn is blown over the aphid via a glass tube. The electrode sends the signal to an oscilloscope. A chart recorder independently notes the output from the gas chromatograph.
Now, if we draw the gas chromatograph over to allow the effluent to pass over the insect's antenna, we will then get an electrical response when we have a biologically active component leaving the gas chromatograph.
And here's the result. Of all the compounds present in the sample, just one causes this frenetic response. The peak on the chart recorder identifies the chemical responsible, so we can use the mass spectrometer to find out exactly what that compound is.
If we return now to the gas chromatogram, we know that the biologically active peak is on the time scale at 890. So if we obtain the spectrum for that, now we can start to determine the structure of the molecule involved.
The top graph is once again the output of the gas chromatograph, but now we know which of the peaks is due to the alarm pheromone. The bottom scale shows the mass spectrum of that chemical. The mass spectrometer has broken the molecule up, and each peak represents a fragment of the molecule. The numbers are the masses of the fragments.
The other features of the mass spectrum come from the fact that in the source of the mass spectrometer, the molecule, under the ionizing influence of the electrons, breaks up and gives fragments which allows us to piece together the whole structure. And from this information, we deduce in this case that the molecule is a beta-farnesene.
Beta-farnesene is a hydrocarbon with this rather complicated-looking structure. It's not a new compound. It's also found in certain plants and has been known for many years. The complex analytical equipment has identified the compound as a beta-farnesene. But the detective work isn't over yet. Recall the isomerism based on double bonds in the middle of organic molecules. Double bonds are more rigid than single bonds, so molecules like this can have two quite distinct forms. Beta-farnesene is another such molecule. It has chains of carbon atoms on either side of the double bond, But the same principle applies as before. The molecule can have two distinct shapes, called isomers, depending on the precise arrangement of the groups attached to the double bond. Is this difference important to the insect? Further testing with the two forms of beta-farnesene shows that, at the molecular level, the receptor on the aphid's antenna has a very specific shape. Only the form known as trans-beta-farnesene fits. The other form doesn't, and won't evoke a response from the aphid.
Here we can see that a biological system only responds to one particular isomer of a molecule. It's important then, in developing such materials for agriculture, to use processes which only produce the particular isomer of interest. And finally, so as to minimize the amount of chemical that's being put into the environment, it's necessary to know which isomer is active and only use that one.
So, trans-beta-farnesene could soon join the thousands of organic chemicals which underpin almost every contemporary human activity. Each of these substances has, in the past, undergone a phase of development and testing similar to that of the alarm pheromone. Once past that stage, there is a need for manufacture on a routine basis. With so many diverse and often complex substances routinely required for applications in anything from agriculture to the production of medicines, and in quantities ranging from grams to tons, how are they made? It's companies like this which manufacture organic chemicals on the required scale. Genzyme Fine Chemicals, here in Suffolk, produce a wide variety of compounds, mainly for use in the healthcare field, some of which they market themselves, others which are tailor-made to a customer's own specifications. The main production area is basically a factory building in which the equipment is simply a number of large-scale reaction vessels which can produce the quantities of chemicals required to satisfy commercial demands. The principles of production that are adopted here are no different to those used on the laboratory scale. It's simply that the quantities of the reactants used are different. Smaller batches of high-quality, high-value compounds are produced in equipment which is more identifiable as conventional chemical glassware. And some of the chemicals are made down at the laboratory scale. One chemical made here, which again has isomeric properties, is glycidyl butyrate. It may seem complicated, but in fact it is put together using the functional group approach to organic chemistry. Glycidyl butyrate is an ester. That is, it contains this functional group. One way to form an ester is by the reaction of a carboxylic acid and an alcohol. These combine to produce the ester, giving off water as a byproduct. This reaction is rather slow and can be speeded up by modifying the acid to make it more reactive. This is done by first reacting it with thionyl chloride. This replaces the hydroxyl group with a chlorine atom to give an acid chloride, and at the same time releases hydrogen chloride and sulfur dioxide as gases. This acid chloride is much more reactive than the acid itself. The colourless thionyl chloride has been added to the colourless butyric acid, and the two are mixed. What happens next? Well, not much, as the reaction is very slow at room temperature. Heating the mixture speeds it up. With heat, clouds of vaporized chemicals soon fill the flask. They try to escape up the condenser, but the cold water, which is constantly circulating in the outer glass jacket, causes them to condense as droplets, which run back down into the mixture. The reaction is so slow that even with heating, it isn't complete until the following day. The brown coloration is not due to the products, but to impurities in the original chemicals. The butyryl chloride must be separated from this mixture, and this is done by distillation. The condenser has been turned round, and the butyryl chloride vapor is allowed to escape, condense, and run down into a separate flask to be collected in a pure form. Now the butyryl chloride can be reacted with the alcohol glycidol. The reaction takes place very rapidly, giving off a molecule of hydrogen chloride and forming the ester glycidyl butyrate. At room temperature, the reaction starts immediately and vigorously, giving off a great deal of heat. If it were left alone, the reaction mixture would heat up so much that the glassware might shatter. So, dry ice, solid carbon dioxide, is added to the yellow-coloured liquid in the cooling bath to control the reaction. The byproduct from the reaction, hydrogen chloride, gives rise to white fumes which fill the flask. The reaction is finished after a couple of hours. Byproducts have been deposited as pink-coloured inorganic salts, which are washed off with water. Now, the glycidyl butyrate has to be separated from the mixture. With the added water, there are two distinct layers. One water-based, floating on a denser brown organic soup containing the impure glycidyl butyrate. These two layers are separated by drawing off the lower layer. The glycidyl butyrate will then be purified. But this isn't the end of the story. Glycidyl butyrate has isomers. The isomerism here results from the arrangement of groups which are attached to a carbon atom. Whenever carbon is attached to 4 different atoms or groups, the resulting molecule can exist in 2 forms. Holding a mirror up to the model helps to illustrate this. The mirror image represents a different form of the same molecule. However much the model is rotated to try to make it identical to the mirror image, only 2 of the groups will ever be in the correct position. The other 2 will always be in different places. Here, the orange and violet atoms match, but neither of the others. Here, green and white. No matter which way the molecule is turned, it cannot be made to fit the mirror image. So this molecule exists in 2 forms. One, the mirror image of the other. Molecules with this property are said to be chiral. Glycidyl butyrate has this property. One of the carbon atoms in the glycidol molecule is attached to hydrogen, oxygen, a single carbon, and finally a carbon with a hydroxyl group. As this carbon has 4 different groups attached to it, the molecule is chiral, a property inherited by glycidyl butyrate. Both forms are made in equal quantities during the reaction, but because of the different shapes of the 2 forms, only one of the isomers is useful. Glycidylbutyrate is used in the preparation of drugs administered to control blood pressure. Like insects, human beings respond very specifically to different isomers, and in this case, only one form of the drug has the desired effect. The other is not beneficial and so needs to be removed. How are the two isomers separated? The key to the separation is this variability of living systems to distinguish between two isomeric forms. The method involves using an enzyme, a biological catalyst, here added in a powdered form. This, because of its molecular shape, attacks only the unwanted isomeric form. Sodium hydroxide is also added because what the enzyme does is the reverse of the previous reaction. It attacks the ester, reforming the original butyric acid and the alcohol. As the acid is released into solution, the pH falls. The enzyme can only work within a narrow pH range, around 7. The sodium hydroxide, which is a base, reacts with the butyric acid, lowering the hydrogen ion concentration, so maintaining a sufficiently high pH for the enzyme. At room temperature, all the unwanted isomer is removed in a few hours. Finally, a check is made to ensure that all the unwanted isomer has been removed. A sample of the active glycidylbutyrate in solution is tested for purity using a polarimeter. Isomers with a chiral center have the property of rotating plain polarized light shone through them. The glycidylbutyrate is placed in a cell which is inserted in a light-proof chamber. The amount that the sample rotates the light, here measured electronically, is a characteristic signature of the molecule. In this case, minus 0.29 degrees exactly. The product is now in a pure form, which can go on to be used in the manufacture of beta blockers for the control of heart disease. Freedom from hunger and disease are perhaps the most fundamental of human aspirations. We have seen 2 examples of the role of organic chemistry in fulfilling these aspirations. The search for environmentally sensitive methods of pest control is a prerequisite for ensuring a secure food supply. The development of new and more effective drugs for the treatment of disease relies heavily on the skills and ingenuity of organic chemists. And in both the examples shown in this program, the relationship between the uses of organic compounds and their molecular shape has played a crucial role.